Hello, my name is Peter Martins, and for this mini presentation, I decided to tackle exam question 25, which asks to briefly describe the 5 neuroimaging techniques from table 9.1. Before we move any further, I want to get some basic definitions out of the way. We must first ask, what is the technique measuring? There is electrophysiological techniques that measure electric fields of neurons as they release action potentials, and examples of these are single unit recordings, EEGs, and MEGs. There's also metabolic techniques that measure the circulatory supply of oxygen and glucose to the brain, and more so measuring the metabolic cost. An example of these techniques are PET scans and fMRIs. There's also a differentiation between anatomical, functional, and affective connectivity. Anatomical connectivity is more so measuring the anatomy of the brain, and these can be MRIs or CT scans. Functional connectivity is more so measuring the patterns of correlation between the functions of various brain areas, and these are more so fMRIs, PET scans, EEGs, MEGs, and single unit recordings. And then there's affective connectivity, which is the latent structural model of a causal information flow within the network, and these arise from the combination of anatomical and functional connectivity. There's also the question of asking how to refer to these neuroimages in terms of resolution. There's spatial resolution, which refers to the number of pixels or voxels that are used in the construction of a neural image, and these techniques have the ability to tell you where in the brain neural activation occurred. There's also temporal resolution, that is more so the discrete resolution or detail of a measurement with respect to time, and this is the technique's ability to tell you when neural activation occurred. There's usually a trade-off between having good temporal and good spatial resolution, and this is due to various reasons, such as various laws of physics and the state of technology that we're at today. The first neuroimaging technique I wish to cover is single unit recordings. This is an electrophysiological technique that measures functional connectivity, and this involves inserting microelectrodes into brain areas of interest, and these measure local field potentials, which are the electrical potentials of extracellular space in brain tissue. And to get data, you more so compare this data to your baseline activity. Pros of single unit recordings are good temporal resolution. It's because the parastimulus time histogram gives instantaneous firings, as well as good spatial resolution. The cons are this is intrusive and only able to record from less than 100 neurons at a time, which is disheartening considering there are 86 billion neurons. The next neuroimaging technique I want to cover is electroencephalography, EEGs. This is electrophysiological technique that measures functional connectivities. This involves electrodes measuring the summed electrical activity of millions of neurons in the form of oscillatory activity with different frequency bands. This is because voltage fluctuations are resultant from ionic current flows within the brain. Pros to EEGs: it has good temporal resolution within milliseconds, continuous spontaneous recording, so you can record data for hours on end, and EEG data can be combined to form ERPs, which is a very powerful tool within neuroscience. Cons to EEG are it has poor spatial resolution, and this is due to the inverse problem of source localization via dipolar analysis. So it's basically hard to tell where in the brain neural activity is occurring from the EEG data. Magnetoencephalographies, or MEGs, are a electrophysiological technique that measures functional connectivity and measures magnetic fields from the same electrical occurrence as EEG. This has better spatial resolution and less distorted than EEG millimeter precision. This is because the skull is transparent to magnetism and not electricity. It also has good temporal resolution, as well as better equipped to solve the inverse problem that I mentioned on the previous slide. However, the MEGs require a special room to block out competing magnetic interference and is very expensive, so this basically leads to it not being all that widely used. Positron emission tomographies, PET scans, are a metabolic technique that measures functional connectivity, and these measure gamma waves from each voxel of brain tissue, and the data can be used to measure cerebral blood flow in different areas of the brain. Pros are it has two PET scans, has good spatial resolution and good for pacemakers and metal implants because they wouldn't be able to use fMRIs or MRIs. However, a radioactive tracer must be injected, and it's more expensive than an MRI, as well as having poor temporal resolution. The final neuroimaging technique I wish to cover is functional magnetic resonance imaging, fMRI. This is a metabolic technique that measures functional connectivity, and this uses electromagnets to measure blood oxygen level dependent bold responses, and this correlates to the average energy consumption within each voxel. And within each voxel, there's millions of neurons. Pros to fMRIs as good spatial resolution, non-erasure and no radioactivity, and the functional connectivity can lead to effective connectivity, and as I discussed earlier in the slideshow. Cons to fMRIs as poor temporal resolution and takes a few seconds. This has been my presentation. I hope you guys enjoyed.